6.5 is on the concept of work, what's called work. So first we'll look at a constant force for work and its definition. You may have seen this in physics already. If not, you will in physics at some point. So work is defined as W for work is defined as a force F times a distance D, sometimes F times D. So we think of work as kind of like, pushing something over a distance. You've done some work to do it, is where the term comes from. So work is equal to force times distance. The units of work are in foot-pounds. It's like a product. That's how they usually write it. Or Newton meters, which is joules. So it's an energy, basically. So here's a simple example, like a non-calculus based example. Find the work done in pushing a car a distance of 20 feet along a level road, so no gravity and no friction, basically, while exerting a constant force of 90 pounds. So in this case, we have our force is equal to 90 pounds. Our distance, D, is 20 feet. And so simply the product of that is work. So work is force times distance. So that's going to be 90 pounds times 20 feet. And that gives you your foot-pounds. So that's 1,800 foot-pounds is usually how you would write it. Excuse me. We're not interested in, we need to talk about constant force, but what we're interested in, of course, is a variable force over a distance. Because when you get the varying forces, it's continuously varying, and that's when you end up doing integration and calculus and stuff. So let's take a look now at variable force. We'll do a quick derivation of it. All right, suppose a force is given by a function f of x. So suppose a force is given by f of x. We're going to assume f is continuous on a closed interval from a to b. So we'll just say that. So f is continuous on a to b. And so you have some interval like this, a to b, and you might assume, show, whatever. So that's like your x-axis, and your force doesn't have to be like a vertical axis, like showing a force. It's just another force. So it could be graphed in many different ways, but you could. And so it's changing along this interval. So the force is different along each different value of x. So what we're going to do then is partition up the interval x1, x2, etc., all the way to x sub k minus 1, x sub k, right, etc. We're going to, so this little distance here times whatever force it is our delta distance, or delta work. So we're going to say delta W sub k is the increment of work done from x sub k minus 1 to x sub k. And so we're assuming that's one of them, right? Just that piece right there, we'll say is the delta work from here to here. Okay, so to do that, it's going to be the distance times f of x, right? So that's what we'll say. The total work is equal to each of those. Delta W1, W2, and then you add them all up all the way to delta W sub n. And that doesn't give you the exact amount, right? Because it's actually changing within that interval. So we're going to take a limit, just like we normally would. So choose z sub k in the kth interval, x sub k minus 1 to x sub k. Then f of z sub k is the force. At z sub k. So what we have is that delta W sub k is like that in that tiny increment, whatever the increment is, the work's approximately that product. It's not gonna change a lot in that little piece right there. So delta W sub k is just the product f of z sub k times delta x sub k. So then we can then take a norm of the partition, approach 0, and that becomes our definition of work. So work is equal to the limit as the norm of the partition approaches 0, just like everything else before, sum over all the k's, f of z sub k delta x sub k. Okay, and then that equals, by definition, the definite integral from a to b of f of x dx, where f is the force. So let's look at an example, simple example, before we go on to the more interesting ones. So find the work done by a force. So find the work done by a force f of x equal to 1 over x squared, and we'll make that in newtons, along the x-axis from 1 to 10. So along the x-axis from x equals 1 to x equals 10, and we'll make that in meters so that we can have Newton meters. So our work would be what? Well, it's just the integral from 1 to 10 of 1 over x squared dx. And you just evaluate that. So that's going to be equal to negative 1 over x evaluated from 1 to 10. So it's negative 1/10 plus 1, which is, you can put it in a decimal. As long as a decimal is exact, that's fine. But this is application, so we're fine with that. So that's Newton meters or joules. So that's the most simple case you're going to get, is just integrating that. Okay, next we'll look into kind of the heart of this section, and that is pumping liquids from a container. And it varies, right? If you have an odd-shaped container, and we'll do this one first in the next video, and then you're going to pump that liquid out, the force of the water due to gravity changes the shape of this changes. Force is always the same, but you have different weight on that slab versus that slab of water. So it varies as you lift it up and out. So we'll talk about that next time. Okay. See you soon.